So this is a short discussion on the material in section 4.9, which is one of the more important topics in the course. We're going to actually take we're going to reverse the process of taking a derivative. It's called an antiderivative or an integral. And it's something you'll be using. If you're going to take Calc 2, you really need to know. And also, we need to know this for chapter 5, which we start, I think, next Thursday. And all we're doing is we're just reversing the derivative, right? So here's an example. Look at that example 1 right here. And suppose we take the derivative of 1/3 x cubed plus 6x squared minus 4x plus 3. So we get this function here, x squared plus 12x minus 4. So this capital F right here is called the antiderivative well, we're defining it as lowercase f of x right here. So, okay, so someone said, hey, what's the antiderivative of x squared minus 12x minus 4? Well, a possible answer is 1/3 x cubed plus 6x squared minus 4x plus 3. When I say there's actually many solutions because you take the derivative of a constant, you just get 0. So you can actually add any constant to this f of x, and it'll be the antiderivative of x squared minus 12x minus 4. Okay, or this function right here. So we're just going backwards now. So we've done a lot on how to take derivatives of trig functions, derivatives of functions in the form of x to some exponent, and now we're just reversing the process. So okay, so here's another problem. What is the antiderivative of 2x? So what function has a derivative of 2x? Well, we know it's x squared, right? You take the derivative of x squared, and the derivative is 2x, right? But also but notice also x squared minus 20 has a derivative of 2x. X squared plus 3 has a derivative of 2x. So in general, if someone said, hey, what is the antiderivative of the function f of x, lowercase f of x equals 2x, we'd say it's x squared plus c, because really there's a whole family of functions whose derivative is 2x. Okay, so here's, in case you've never seen this before, here is the notation that we use. So if someone says the notation for antiderivative, so we actually there's this symbol, this integral symbol right here, and we put the dx on it. Okay, so integral f of x dx means what function has a derivative equal to lowercase f of x. So here's just a few rules. And I think this unit is really not too bad. Plus, you'll definitely be able to have notes during the test. Even if it was this was a proctored exam in the classroom, I would, most teachers allow you to keep like a page full of notes. So, so like the derivative of a constant k, well, it's just kx plus c, right? You take the derivative, right? The derivative of x to the first is just 1. Right, so you take the derivative of kx plus c, and the derivative of c is, constant is 0. So you just get k. So like the antiderivative, the integral of 7 right here, the integral of 7 or the antiderivative of 7, and here the variable is dt. So we'll use t as the independent variable. So the integral of 7 dt is 7 times t plus c. Make sure you add on the constant. It's not correct to say the integral of 7 dt is 7t. It's an incomplete answer. So this is incomplete. You need to add that constant, or else you're really not being correct. Okay, so here's another one. We'll just say we just have integral of dy. Well, there's actually a 1 here, right? But so one is one of those invisible numbers, right? Normally we don't write 1 times dy. We just say dy. But the integral, but what function has a derivative equal to 1? And again, the variable is y. So we just say y. So the antiderivative or the integral of 1 is y plus c. Okay, so now here's a really important one too. Okay, the integral of x to the n, right? Okay, so we know that if we take the derivative, right? So if you take, let's write this over here. So if you take the derivative of x to the n, right? X to the n plus 1 dx, right? What do you get? You get n plus 1 times x to the n. You don't have a lot of room here. Okay, so no, so we have this factor of n plus one. So that's why, so when you evaluate the integral of x to the n, okay, so we know that we know that the derivative of x to the n plus one, we subtract one, we get x to the n, but we have to divide it by n plus one. Yeah, we have to get rid of this term right here, right? So the integral of x to the n is x to the n plus one divided by n plus one. Yeah. So you just verify, you take the derivative of this function right here, you get x to the n, and then make sure you add c. And also, because we're dividing by n plus one, yeah, so n cannot be equal to -1, right? So we're going to learn later. I don't know whether I think you might learn this in Calc 2. And so I've taught calculus, they keep changing the curriculum of what's taught in Calc 1 and Calc 2. But yeah, you'll learn about that later. There's actually a function called natural log of x, and you'll learn about that. So I think maybe we learn at the end of this course or the beginning of Calc 2. Okay, but yeah, definitely important integral. But yeah, so the integral of, yes, so this formula works except for when n equals 1. Okay, so like the integral of x to the fourth is x to the fifth over 5, and then plus the constant c. So now be careful. Okay, so let's say here we have 1 over the square root of t. So I would always, so whenever you have these square roots or like cube roots or something like these root functions, just convert it to exponent form. And then you just add, when you take the antiderivative, you add 1 to the exponent, but just make sure. So you add 1 to -1/2, so you get t to the 1/2, right? But then make sure you divide it by 1/2. So you could, and then you just kind of simplify that. You don't leave 1/2 in the denominator. So you just simplify this. So that's 2 square root of t plus c. Okay, so let's continue here. Okay, so let's say you have k times f of x. You can actually just pull that constant out, right? Because you can just pull the constant out. And so like 3x squared, the integral of 3x squared, so it's 3 times the integral of x squared. And so that's x, so the integral of x squared is x cubed over 3 plus c. And so, and it turns out, so then you actually would just write x cubed plus c. You wouldn't write, see right here, and I think there's actually a subscript 1 there to make that a little bit different. But you wouldn't write like this. So this would be, don't do this. So this is, you wouldn't write x cubed. You wouldn't write x cubed plus 3c. So this is don't do this. You just write it as x cubed plus c, because 3c is itself just some constant. So you see there's like a subscript c1 there to make it different than that c. So yeah, you don't multiply the c by a constant. So the integral of 3x squared is just, again, so the integral of x squared is x cubed over 3. And then you kind of have this 3 here. So these 3's cancel each other out. So it's x cubed plus 3. Okay, so the integral of a sum, the integral of a sum or the integral of a difference is equal to the sum of the integrals or the difference of the integrals. So we can actually split the integrals into 2 pieces. That's really very common. You do that a lot in Calc 2. But again, here, integral of 8p over 3 p to the -2, or 3 to the p to the -2. So just separate them into 2 separate integrals. Make it 2 separate problems again, and then we can pull out the constant, right? And so p to the first, so that's just p squared over 2. And then here you have p to the -2, so you add 1. Add 1 to -2, so you get p to the -1 over -1 times 3/4. Okay. And yeah, so the final answer is 4p squared minus 3/4, 3 over 4p plus c. Okay, so taking integrals of any kind of expression like x to the n dx. So this isn't too bad as long as n is not equal to 1, -1. I'm sorry. So this isn't really too bad. Integrals of x, because we just add 1 to n and then just divide it by n plus 1. Okay, so then integrals of the trig function. And we just have to go backwards. So here you just have to know what the derivatives are. So we know that the derivative of sine is cosine. So the integral of cosine, again, you just go backwards. The derivative of sine is cosine. So the integral of cosine is sine. And then of course you have to add on that constant c. Okay, so integral of sine, well, the thing, remember, it's not cosine, it's minus cosine, because take the derivative, because the derivative of cosine itself is minus sine. So we have to multiply it by -1. So we know that the derivative of tangent squared is secant squared. So the integral of secant squared dx is tangent x plus c. And I think we kind of know these. These are just the right? The secant x, tangent x is the derivative of secant. So the integral of secant tangent is secant x. So to do these integrals, you just have to know the derivatives of the 6 trig functions. And again, you can just keep those notes with you when you're taking a test. Just keep them with you when you're doing any kind of problem, your test or doing homework. Okay, so here let's just look at ones that maybe a little bit. So again, yeah, I do recommend when you look at like this b here. So integral of, so we're going to break this up into 3 integrals. But when you take the antiderivative of 3 over the cube root of x squared, just make sure you write it in exponential form. And then all you have to do is add 1. You add 1 to -2 2/3. Yeah, you get 1/3, and then you divide it by 1/3. And again, don't leave. You don't want to leave 1/3 in the denominator, right? 1 over 1/3 is equal. Isn't that just equal to 1 divided by 1/3, which is equal to 1 times 3, which is 3. Okay, so yeah, so don't leave fractions in the denominator or put them in the numerator. Okay, so you have integral of now there you're multiplying 2 polynomials. So just take the product, right? That's really the only, for right now, that's the best way of doing it. So first we take the product, and then we take the antiderivative of the individual terms. Right here, it's the quotient of 2 polynomials. So just simplify it, right? Break it up into 2 integrals, break up this fraction right here, or this rational expression. So it's x to the 4th over x squared minus 1 over x squared. So and then next, I think it's next semester, you learn all these techniques of integration. Sometimes there are these special rational expressions where you actually don't break it up. And that's the thing about, I will have to say that there's a lot of techniques of integration in Calc 2. It's really, really pretty challenging. This is right now, I think it's not too bad, because really you're just doing the opposite of everything we learned essentially in chapter 3. But there's some special integrals that you do in Calc 2. Yes, can really be kind of challenging. Okay, so here's one. Okay, so again, integral of secant squared x plus 2 cosine x cotangent x. So we recognize. So the important thing is to recognize these are the derivatives of trig functions. We recognize that secant squared is the derivative of tangent, and we recognize that cosecant x cotangent x is the opposite of the derivative of cosecant x. So if you don't recognize that, then it's going to be hard. But for right now, we're not doing any of these kind of tricky integrals that you're going to learn later on. So just where you have to use identities or something like that. So if you see if we're taking the integral of some kind of trig function, it's likely it's just a direct, it's just the derivative of one of the other trig functions. But later on, eventually you get these integrals where you have to use a lot of identities, and it can be a lot of work eventually. So that's why we want to learn this right now. Okay, so so differential equations. So there's courses on you can get, the people who that's their whole life are differential equations. They get their PhD in differential equations. They teach differential equations, and they talk about differential equations all day long. And the whole world is like based on differential equations, like, the way fluids move, and, so differential equations are really quite important. So differential equations, well, I keep talking, I didn't even say what it is, but a differential equation is an equation that involves a derivative. So really a very important topic. And if you like math, or, it's definitely something you'll study. A lot of differential equations are actually solved using, we don't actually get a formula for the differential equation. We actually approximated the solution via a computer. There's a whole area of mathematics called numerical analysis, if you like that kind of stuff. Okay, so differential equation is an equation that involves a derivative of an unknown function. So this is like one of our favorite differential equations, right there. Example 4. When I say favorite, because it's pretty easy to solve, because differential equations can be really, pick up a differential equations book, and you see it's a chapter after chapter of all these techniques of all these, ways of solving different types of differential equations. But this is about as straightforward as it gets, because you just integrate the right side. You take the integral of the right side, or you find the antiderivative of 4x squared plus 3. So again, x to the first, we just add 1 to it, we get x squared, and we divide by 2, right? You get 4, whoops, hello. Can I write a 4? Maybe not. 4 over 2x squared, right? And then plus 3x, and then you have to add this constant c, right? Right, because that's the general solution, right? So there's a whole family of solutions to this differential equation right there. Okay, so we've solved the equation. Okay, so here's another one. And now, so that's called, so that's just a differential equation where we just have some, we just keep the constant in there. Now there's something called initial value problems, where we actually say, okay, so we state the antiderivative, we give the value of the antiderivative at a certain point. So like here, so let's say we want to solve this differential equation. Again, another one that's really not too bad because it's y prime or f prime of x 4 over the square root of x. But remember, that's just equal right here. You just can rewrite that square root as x to the negative 1/2. Okay, so you add 1 to negative 1/2 and you get 1/2, and you divide, right? So you're going to divide 4 by 1/2 and you get 8. So that's where that 8 comes from. So the general solution to this, in example 5 right there, the general solution is 8 times the square root of x plus c. But we're given an initial condition, right? So your f of x, okay, so we know that f of 1 is c. So when you plug in, f of 1 is c, f of 1 is 3, right? Okay, so when we plug in 1 into this formula, y should be 3. So the solution, the function whose antiderivative, and the function whose derivative is 8 times the square root of x, we know when we plug in 1, we should get the y value is 3. Okay, so you just plug it, so we just solve this equation right here. So you plug in 1, or you substitute x1, and the value of y should be 3. And so you just solve this, so you just solve now you solve for c, and you get that c is negative, right? 3 is equal to 8 plus c, or so c is equal to negative 5. So, so the solution to this initial value problem is y is equal to 8 times the square root of x minus 5. So in other words, you take the derivative of that function on the right, you're going to get 4 over the square root of x, and you substitute, when x is 1, the value of y is 3. So the one thing you'll learn if you take a differential equations course, that this is called a particular solution. Some of the words they use in math, I don't know. Mathematicians have a way of talking, but anyway, yeah. So when we're solving an initial value problem, the solution is called a particular solution. Okay, and differential equations are really very important in physics. So like we know that, so let's say S is our position function, like they're in example 6. Well, the velocity function, so like the velocity function is z, or v of t. We know that v of t is just the first derivative of the position function. And we know the acceleration is the derivative of the first derivative of the velocity, or the second derivative of the position function. So there's an example where differential equations, come into play. Okay, so okay, here, so a ball is thrown upward with initial velocity. So you have an initial value. So you're throwing the ball up, and the initial velocity is 100 feet per second, and the initial position is 50 feet. So v of 0 is 100. And S of 0 is 50. And so find the position function that gives a height as a function of time. And the acceleration, gravity, is just a constant, minus 30, because it's going downwards, minus 32 feet per second squared. So up is positive, and down is negative. Okay, so to get the velocity, right? Remember, so the velocity is v prime. Remember, the velocity is just the derivative. The velocity is just the acceleration is the derivative of the velocity. I'm sorry. So v of t, so a of t, that's what I wrote here. So a of t is the velocity Okay, so a of t, which is, so the first derivative of the velocity is minus 32, right? So here you have so here's a differential equation that's, kind of a real life differential equation. The acceleration, which is the change in the velocity, is minus 32 feet per second squared. Okay, so to get the velocity, we have to solve the differential equation. V prime of t equals negative 32. And you take a physics course, I'm sure that you see this a lot. This is kind of one of the most basic differential equations you see in any kind of, applications. You're learning applications of differential equations. This is really one of the most basic equations that you see. So you take the integral of negative 32. So you get the velocity is negative 32 t plus c. And we're told that when t is 0, the velocity is 100. So how do we solve for c here? So when t is 0, c is 100. So you get, so you just plug that in here. So you solve the equation. 100 equals minus 32 0 plus c. C is equal to 100. So the velocity function is minus 32 t plus 100. And now the position function, we know that s prime of t is the velocity, right? We know that s prime of t is now 32, and we know the velocity function is 32 t plus 100. So to get the position, we just solve that differential equation right there. Okay, so we just integrate, right? We integrate minus 32 t plus 100. Again, add 1, so that's t to the first. You add 1 to it, and divide by 2. So you get minus 16 t squared. And the integral of a constant is, the integration variable is t, so it's 100t plus some constant k. Except we're given the initial position. We're told that at time equals 0, the position is 50, right? So when you substitute 0, so here's this is s of t, and we know that s of 0 is 50. So you just solve this equation right here. 50 equals minus 16. 50 equals minus 16 times 0 squared plus 100 times 0 plus k. So k is 50. So this is the position. So we've actually solved the problem. Okay, so if a ball is thrown with an initial velocity of 100 feet per second, and a height of 50 feet, what is the position function? Well, this is the position function right here. It's minus 16t squared plus 100t plus 50. Yeah. So you plug in s of 0. Yeah. When you plug t equals 0, s will be 50. And what's the velocity at t equal to 0? You take the first derivative, right? And you'll get minus 32t plus 100. So the first derivative is 100 when t equals 0. Okay, so I think I'll let you read some of the other, read this second application on your own, and I'll just stop the recording.